Alright, this is my senior SPED talk. This is for my senior project, CS499. I'm going to talk a little bit about embedded systems and what they can teach us about building efficient software. So this is a Genesis map scrolling demo that I have up here. And for those of you who are not familiar with the Sega Genesis, it is a 16-bit console that was released back in 1989 in North America. It has 64 kilobytes of system memory and 64 kilobytes of video memory. And what you're seeing over here is plane B of the video memory, because the Genesis has video displays split up into two planes, so plane A and plane B. And as you can see, as I scroll around, it updates the tile map interactively, and this is just plane A right here. Plane B, which is the background, which is far more interesting. You can see it start updating there, and notice how that when it is updating each tile, it only calls the tile that it needs to, in this case the one that is outside the screen border. So how does this all work? This is embedded C. This is what I use to develop my game on, which is my senior project is a 16-bit game for the Genesis. This is a modification of KCO Wolf that he used for his scrolling demo. And I just want to point out a couple features with this code. So with embedded systems, like systems like the Sega Genesis, the Motorola 68000 is the CPU which is used in that system, and it is also used in a wide variety of different microcontrollers and different microarchitectures. One such example would be the PowerPC architecture, but PowerPC is also kind of fallen by the wayside, so we may see the death of 68K architectures, at least in mainstream platforms, but I think they'll still continue to live on in microsystems. So let's take a look at the scrolling map initialization function. This is where information about the map is fed, and as you can see here, the offsets for the array that I'm using to feed all this information to the engine are being computed right here, and so they're all being multiplied at the start, because multiplying during the operation or screen update is very expensive, and that's one of the first things that you'll start to appreciate with embedded systems. You'll start to realize the importance of keeping your operations as simple as possible, as linear as possible. I'm only doing a one-time multiplication of the offsets here at the beginning. And a really good demonstration of this, a way that you can conceptualize this, is by looking at the sprite work that I'm going to use for my game. Let's take a look at the car first, because this is a little bit more interesting. So as you can see here, I have these grids. This splits up the sprite into 8x8 tiles. The way that the Genesis understands this particular sprite is it's being fed these 8x8 pixel tiles, which are represented by this this unsigned 32-bit array. These numbers right here represent a cell, and each cell has 32 bits per pixel line. And this is one of the other things that you'll start to appreciate when you start working with embedded systems, is that a lot of the obfuscation that we use, a lot of the abstractions, they don't really work here with embedded. Incorporating those types of mindsets is pretty expensive to the machine and to the compiler. So everything that you do, everything that happens inside a computer, it's represented with binary. Numbers themselves are kind of an abstraction, but you see what I mean. This is kind of the reason why I love embedded systems, is because it forces you to think in the most minimalistic terms that are possible. You start wondering to yourself, oh, can I do this? Can I do that? With embedded systems, you start thinking about, what can I do with or without? You start asking yourself, what can be stripped away to leave the minimal functioning that you need in order to accomplish your task. So I hope that was kind of an insightful look into what embedded systems looks like. It's something that I hope to do as a career, and I hope you enjoy.